All right, let's go.
Morning again. Is everybody getting my slide?
Yes.
I want to know if you are getting my slide.
Yes, we are. You can see the
Okay.
slides.
Yes, thank you, thank you. I'm here by the name of Jean-Claude Hakizimana. I'm gonna give you a brief, comprehensive review on electrochemical cytokine detection in Sweden. Yeah, first of all, last time we were just discussing more about cytokines as the small protein that are used for signaling molecules. So therefore, their detections can lead to the determination and the analysis of different diseases. So today we are going to give you a glitch summary about what I have already seen in the paper that were given. So let me start on showing you this person, the image that I'm going to show you on here. I think everybody is looking. This is one of an example for a wearable electrochemical biosensor. So actually, first of all, in the paper, the authors tried to show different mechanisms, how really those electrochemical biosensor works. Me too, that is where I'm going to start. I'm gonna show you how those electrochemical biosensors are seen. As you see on the first line, we have what we call the microfluidic biosensor, which is used to detect, to have the inlet and outlet. Down there, I have also what is inside this biosensor. We have different components. As you see, we have the biorecognition elements, which detects with the cytokines, the target molecules, and also we have the non-target molecules, of course, and also we have the electrolytes, and also the transducer, which is where they are attached. This is the one which will convert the electrical signals, the chemical signals into electrical signals that can be amplified and displayed and analyzed, of course, so that they can show what's really going on. Again, this already, it is what led to the example for a wearable electronics a device that may need like a Wi-Fi so that they can get information. They can those information they can pass through the different stuff like a Bluetooth. They can use Bluetooth, of course, or Wi-Fi so that the information can be shared well. And again, within the papers we summarized, we have also seen different papers. They review different techniques, different biorecognition elements, different stuff. Let's see them according to what they have already seen. They have seen different parameters like their sensing platforms, their detection methods, the recognition elements, and most detected false cytokines. So the most sensing platform that were detected in that paper, the review that I have already made, it's what we call electrochemical sensor. This electrochemical cell, it was the first that I have already used, and it have two main classes like two electrochemical cell. That was the first to be used, but also after it used to use the free electrode that is made with the working electrode and the reference electrode and also the counter electrode. The working, it is the one where the reaction will take place and the counter will stabilize so that there is easy detections of the changes, the chemical changes, or the current flow, the electron flow, depending to the detection method that I have already used. And again, they have tried to detect by using different detection methods, uh, like uh, EIS, what we call electrical impedance spectroscopy. This was already the first one that I have already used in that detections. And the different other techniques were used, like cyclic volumetry, conductometry, differential to stage. But this one, electrical impedance spectroscopy was the first one because it is very selective, and also it have the ability to detect the small concentration, the low concentration of cytokines in the sweat. We're gonna continue on the different biorecognition element that I've already used. Of course, the first one that I've already used was the antibody. The Y proteins that have the binding site. And this antibody, actually, the reason why they have already used the ophthalma, it's because the antibody, they are very sensitive, of course, but also as well as they are available on the market, they have low cost compared to the ophthalma. And this ophthalma, it is the DNA strand or RNA strand that is used to detect different molecules, the proteins, the cell. And also this one, it's very sensitive and it can be the best choice for the wearable biosensor because they have the high affinity, the high binding affinity. And again, this aptama, but it's very expensive because to synthesize them, it's very expensive. They use what we call Selex plus Selex method, and that is why it's very somehow it's very expensive. Again, different cytokines, according to the authors, they show that different cytokines have already analyzed what we call single analyte analysis. Like this interleukin 6, that was the first one to be analyzed, and the second one was the tumor necrosis factor alpha. This one was the second, and the interferon gamma, that is responsible for the viral interactions. So those was the top three. Normally, they already detect more and many different cytokines, but those was the first one. But also, according to the research, they have already showed that the analysis of single analyte, it's not enough to take the conclusion, the final conclusion about the disease or for diagnosing the disease. So they also recommended to try to do multiple analytes detection so that they can take better decisions. And that multiple analytes analysis somehow hard. We require the coordination, many complex bio recognition elements, and also somehow hard to make the analysis because each one will have its own band or its own sign, and somehow hard to differentiate them. Again, finally, I'm gonna show you some challenge the concentration of cytokines because actually if the concentration of cytokines in the sweet they are somehow slow, and I see that I may have the problem for internet. Don't know if you are still getting me. Selectivity of biosensor to avoid interference from other sweets, and again some biosensor they have the problem of lack of to be selective for the specific analyte. They can be disturbed by either different metabolites that is found in the sweet, like because the sweet is composed with many components like the hormones, the metabolites, the ions. So different
Yeah, I think Jean-Claude ducked out because probably the internet is not great. Um, all right. And by the way, his time is up. So who goes next? Jean-Paul. You're the next.
Okay, thank you. Are you getting me?
Yes.
Okay. So
Yes.
let me share the screen. Okay. Good morning once again. So as you see, Jean-Paul HARERIMANA, I'm going to present about the electrochemical cytokine detection in sweet. Announcing with an introduction, we've seen that the paper that biosensor is an analytical device that is usually used to convert the biological responses into a given electrical signal. The sweet is taken as one of biofluids that can be used as an analyte during that purpose of using biosensors. It can be used also as a way of real-time health monitoring, especially to detect certain kind of disease in the human body. They use mostly the electrochemical methods where they detect a certain molecule like cytokines, one of the certain molecule that is present in that sweet, and this will serve as a biomarker and an indicator for the physiological and the pathological state of the body. So in paper, they mentioned that the sweet is mostly selected because it is highly similar in composition, like blood. So it is an idea to be used as it is easily collected from the surface of the body without creating the discomfort associated with blood sampling from human body using some needles and other equipment that are discomfort human being. So it highlighted, applied the controlling that the condition in case of different diseases. So like the sepsis condition, I think this is the condition where the bacteria, they reach in our blood system, the diabetes, and even the cancer. So these biosensors, most of the time, they use the antibodies and the appometers as the recognizing element, or they are probed during analysis of biosensors. So these appometers are the synthetic DNA and the RNA molecules that are highly applied here in biosensors. Antibodies are those part of protein that form the body, and they use it to detect specific antigens. Without delaying, I will continue with analyzing some key electrochemical cytokine detection methods that goes through in the paper. Here I will show some advantages and limitations, as well as the detection limit that's highlighted in the review. The first one, it is the electrochemical independence spectroscopy, commonly referred to as EIS. This one, it is based on measuring the resistance to alternative current. It is most advantageous due to its higher sensitivity, and even it doesn't require the labels like the fluorescence and others that can be attached for detection of results. And most of the time, it is suitable for low concentration of cytokines. It's found also that in sweet, the concentration of cytokine is low compared in other biofluids such as blood. But other key limitations, most of the time it requires to have a stable condition, as well as being sensitive to electrode setup and environmental conditions in analytes like the temperature and the ion concentration. That is the detection limit that is highlighted. I may shift to the field electric transistor, the one which is based on passing the electric fields in the analyte. So this one is mostly advantageous as it allows the real-time detection of certain condition, and also it is high sensitive in low concentration. But also it requires a careful calibration, and most of the time it is affected by the physical parameters of the analyte, like the sweet pH and even the change in the temperature. Also, that is the detection for this, the detection limit. The third, it is the cyclic rotametric CV and the chronoamperometric, which is mostly based on the measure of voltage associated with redox reaction that occurs during the analysis of the samples. So it is commonly applied in a laboratory setting, and it is used for multiplex detection. And also it displays the quantitative measures after detection of certain analytes. But its drawback include the low sensitivity during the measurement, and it has less effectiveness on low concentration of cytokine. So also it is highly sensitive to environmental condition. So the detection limit of this is high, mostly compared to the first two methods that are analyzed. So the fourth one, it is the 3-electrode system, which is with the specific labeling SWV. This is SWV refers to the square wearable voltage, the squared wave voltage, and which is simultaneous, used in simultaneous detection for multiple cytokines. And as this can allow the differentiation of different signals, it can be used in detecting of different substances at the same time. So its disadvantages or limitation, it has a high expensive and complex, and most of the time it requires the specialized equipments and the personnel to operate them. So let me shift it to the materials and used in the construction of this above mentioned electrochemical method. They highlighted the gold nanoparticles and graphene and others, that because they are believed to have the conductivity and biocompatibility and stability during this. So those electrochemical are highly applied in the tracking of immune response levels and different infection indicators. So they become critical for proactive monitoring of different diseases. So let me conclude by highlighting that the sweet electrochemical cytokine detection have been taken as the breakthrough for non-invasive health monitoring. However, the low analyte concentration and interference with other sweet components has been highlighted as challenges or throwbacks toward the productive system. So the paper ends up highlighting that future researches should focus on how the sensitivity of electrochemical cytokine detection methods should be increased, as well as the integration of different wearable devices for continuous monitoring of specific health condition. So thank you for your attention. And if you have a question, you might ask.
Thank you. It's time for Pacifique. Go ahead.
Okay, thank you. Let me start by sharing my screen. Good morning, everyone. Hello.
Morning.
Are you able to
Hello.
see my slides?
No,
No.
Not?
no.
Okay, let me check again. Okay, I think now they are visible.
Yes, they are visible.
Okay, thank you. So I'm going to present about paper summary, which is entitled Comprehensive Review on Electrochemical Cytokine Detection in Sweat. So the authors are Moritz Brunner and the others, as you have all seen on the paper. So by proceeding on the general introduction, I'll be talking about cytokines, and many of us have already worked on it. Mainly, cytokines are defined as vital signaling protein present in body fluids, playing crucial role in immune response and disease diagnosis and monitoring. So in the case of sepsis, there is some counter reaction that may lead to the release of some cytokines in response to the presence of a certain disease or sepsis, or in the case of cancer. So, so when you talk of the sweat, it has been suggested that as this possible sampling material where we can detect cytokines, because it has shown that it can also have some protein components that are similar to the blood. So cytokines can be also regarded as the biomarkers, where you can find some of the cytokines that are released in response to the certain disease. So once we try to classify them as biomarkers, we find that they are classified into three categories, which are pro-inflammatory cytokines. Those are cytokines that are released before the inflammation. So they can be they can be released as the signal that if there's an occurring inflammation later. And in that case you can find interleukin 1 alpha, interleukin 6, and tumor necrosis factor alpha. And the other category, which is called anti-inflammatory. It means the inflammation has already occurred, and this cytokines is released as the response to the existing inflammation. And in that case, you can find interleukin 4, interleukin 10, and interleukin 11. And there's the other category of chemokines. In this case, we talk of those cytokines that occur to help in the movement of certain cytokines. And in that case, we find monocyte chemoattractant proteins, monocyte inflammatory proteins. So once we try to look on how the cytokines can operate and affect different systems, we can talk of some mechanism like pleiotropy, reductance, synergism, and antagonism, and cascade induction. In pleiotropy is the case where a given cytokine, like a single one, can affect a multiple targets and response. And for the case of reductance, it's a lot of cytokine that can influence a single response. So there are a lot of cytokines, but they will cause a single response. So for the case of antagonism, this is the case where cytokines will provide opposing or inhibitory signals. So let's talk a little about the electrochemical detection in cytokines in sweat. So once we talk of electrochemical detection, we mean highly sensitive biosensors that combine electrochemistry with biological recognition to detect specific biomolecules. So, in some of the example of those biorecognition elements, you can talk of aptamers, and that is in the case biorecognition element is a single-stranded DNA or RNA. So those biorecognition elements will be there to bind to a given antigen. That particular antigen that you are talking about is that cytokine which is released in the sweat. So those biorecognition will be specific to a particular cytokine element. And for the second, we go for immunosensors. So when we talk of immunosensors, we mean antibodies. And this one that has immunosensors, they almost work in the same under same fundamental principles as ELISA, enzyme immunosorbent assay. And for the third case, we have aptasensors where we combine aptamers, and they are like tumor necrosis factor alpha, and this one is said to have a higher sensitivity compared to the rest. And so this table is going to show us some roles of cytokines in physiological and pathological levels. So it means once you detect this particular cytokine, it means there is an associated pathology. Like for the case of interleukin-6, once we detect interleukin-6, it means there's the possibility of Alzheimer's disease, cancer, or sepsis. And of course, they are detected in a certain amount. So we can also talk about tumor necrosis factor alpha, and it has a certain role in cell signaling immunity. And once you detect this particular cytokine, it means that the chance of arthritis, psoriasis, or COVID-19. So for the case of interferon gamma, it means that once you detect your interferon gamma in the sweat, it means that there's possibility of nematode, arthritis, and cancer. So the second table it talks about specific recognition element that can be used when designing a biosensor to detect a particular specific cytokines. Like for the case of tumor necrosis factor alpha, the suggested recognition element is aptamers, because they have shown a high sensitivity to tumor necrosis factor alpha. Then when you go for sensing platform, I'll show in the design where the sensing platform is placed when designing biosensor. The suggested one is FEIT. And for the case of interleukin-6, the suggested biorecognition element is aptamers and antibodies. And the suggested sensing platform is FEIT, 2E, and 3E. And once I mean it means the electrolyte. And for the case of interferon gamma, we have aptamers and antibodies. So these two figures mentions how the biosensors are designed. So for the symbol A, we have transducer and electronics. So generally the figure of the electrolyte, the figure of the biosensor can be firstly set as mentioned in A. Like you may have the reference electrode, working electrode, and you may also have a thiolinker. And above thiolinker, that's where you attach a particular antibody, and that is for the case of once you select your by recognition element as antibody. Then on the top of that antibody, we put a label that will show the signal when the targeted antigen is detected. So on the surface we have substrate, and then you have the recognition element, then you have electrolyte, which is regarded as the sea of electron that will help us to transfer that information and then display it on the screen as the results. So let's go to the next slide. So some of the signal can be read in the term of the chart. Like for this case, we have impedimento signal response that will show impedance and the concentration of the antigen in the sample. Like for this case, the targeted cytokines were interleukin 6, interleukin 8, and have shown a particular impedance, and that particular impedance will be proportional to the amount of that cytokines in the selected sample. So that's the overview of how electrochemical sensing elements works in the sweat. But before you start to test your sweat sample, there's some of the suggested way of preparing the sample, because they have seen that sweat can be mixed of different elements like metabolites, ions. So as the part of preparing your sample, what you do, there's some buffers where you can place your sample as the way you're preparing it, like PBS. And as the other precaution, before you start using your biosensor, how to first calibrate it. Make sure that is ready to record the standard and collect results. And to test the standard or to calibrate your biosensor, you have to use a reference samples. The sample that you know that they only contain a particular cytokines without the mixture of others. And then you have to dissolve it in that suggested buffers like PBS. So that's marks the end of my presentation. I can thank everyone. Thank you.
Let's go on, Nkunzimana. Yeah, the next. Nkunzimana, you're next.
Hello, everyone. Can you hear me?
Yeah, can hear you. Do you want to share a screen?
Yeah. Let me share my screen. Are you all seeing my screen? Okay.
Yes.
Okay. Thank you. I'm here by the name of Nkunzimana Pierre, and I'm going to present to you electrochemical cytokine detection in sweat for continuous of monitoring. Mainly, it was the summary of the review that was provided. So let's start by introduction. Cytokines are biomolecule mainly used in immune system in general, especially in immune regulation. And here, traditionally or usually, cytokine measurement was done by blood test, and it is invasive and is limited to single time use. That's why wearable sweat-based electrochemical sensor offers a non-invasive and continuous monitoring. So during the review, the hypothesis was to review this electrochemical sensor. Those are designed to detect cytokine in the sweat to have a potential to serve as effective tools for continuous and non-invasive health monitoring. The objective was to aim, the objective of the review was to assess the potential of wearable electrochemical sensor for detecting a cytokine in sweat, while emphasizing on the importance of this sensor in continuous health monitoring. So let's continue. We cannot talk about the review without talking about the cytokines as biomarker, because in the key findings, the review shows us how cytokines are critical biomarkers for either disease detection or what. So key cytokines are interleukins, of course, interferon, tumor necrosis factor, and we can't forget about chemokines like monocyte chemoattractant proteins. They all combine the role of immune response formation and in disease states. Then why the review choose sweat as a biofluid is because they correlate with blood cytokine level, which enable real-time health insights. Also, cytokines can be obtained while using non-invasive tools, which is even easily accessible through wearable device. So among the most used cytokine in the review are these: interleukin-6, interferon gamma, tumor necrosis factor alpha, tumor necrosis factor alpha, which shows with particular roles, of course, and their physiological levels. And here on the pathological level, it means that it can be dangerous when elevated or decreased. Here on interleukin-6, it can be dangerous when elevated. Beyond physiological level, it means beyond on 15 picogram per ml. Here, tumor necrosis factor also can be dangerous when elevated beyond this 362 picogram per ml. Here also interferon gamma. Here it can be a problem when elevated or decreased on this physiological level of 18 to 42 picogram per ml. Let's continue on the ways used to detect cytokines in sweat. Here we use some electrochemical detection techniques. Among those techniques, here we have electrochemical impedance spectroscopy, also known as EIS. It uses alternating sinusoidal voltage over a larger length of frequency, mainly 1 Hz to 1 megahertz, at its high sensitivity, and also it was the commonly used. And not only with high sensitivity, but also this electrochemical spectroscopy, it is mainly used with antibodies. Here, let's continue talking about field effect transistor sensor or FET sensors. They are effective in detecting low cytokine construction through voltage changes, especially with they mostly work with aptamers. As we know, aptamers, they are single synthetic DNA or RNA which binds to the specific cytokines so that they can easily be detected. There are also other electrochemical detection techniques such as CV and CA, cyclic photometric, and chronoamperometry. Talking about chronoamperometry, it's normally using two working electrode and reference and also reference electrode by mainly focusing on constant electric on working electrode. So let's continue with the wearable device design. While designing this design, you have to focus on continuous sweat correction, the biocompatibility of your device, and the flexibility around the body to allow comfortability of your device. Then while designing, you have to also focus on biocoordination elements. Here, let's talk about antibodies also versus aptamers. Antibodies, they are available commercially, but they may be limited to the single use, of course. And also on the antibodies, they have larger size compared to aptamers. And here on aptamers, they offer a stability, of course, due to their small size, of course, which can offer the skin comfortable sense, of course, due to their smallness, which can lead to the formation of a comfortable device. Then let's continue to this diagram. Here we are seeing that all the sensors, while manufacturing or producing electrochemical sensor, they have things in common. And among these, there are transducers and biocoordination element, and also this what we can here they call it electronics, or what we can read our response. Among here we are seeing figures A, B, C, and D. On A here, they are showing us these biocoordination elements with contact with the solution which contain, of course, biomarkers and other non-required things. So based on this structure, I'm explaining a little bit how it works. While this biocoordination element, either aptamers or antibody, bind to the certain cytokine, they form what we call EDA, or electric double layer. And the change in capacitance of EDA can lead to the electric signal, which can read through these electronics. And not only formation of EDA, but also they can occur a redox reaction, lead to the formation of either cardiac or non-cardiac process, which can lead to the also detection of which can lead to the formation of electric signal, of course. This P, it shows two electrode method. This C shows three electrode with a counter electrode, which stabilize electric current from not reaching to the working electrode, which mainly so that the constant electric will be focused on a working electrode. Here D shows field effect transistor. So let's continue to the challenges of wearable cytokine sensor. Here we have the current limitations, like it allows single body use because of the for antibodies they used once, so it requires to be renewed. And selectivity issues also, it becomes a limitation. And also there is ongoing research on exploring either they can make a regenerative sensor designed for extended lifespan. And also, as conclusion, cytokine detection in sweat will be a very good way for the real-time and non-invasive health monitoring. Also, they will support personalized healthcare by enabling early interventions. And challenge and progress, although the challenge is selectivity, urban synergy, it still exists, but ongoing research will aim to overcome those broader clinical applications. Thank you. That was my presentation.
Thank you, everyone. So Jean-Claude, I hear you trying to finish your presentation. Is that so?
I can finish my presentation.
1 minute, please.
Thank you. Hello again.
Hello.
Yeah, I can hear.
Yes, are you getting my slides?
Yeah.
Okay. Yeah, I'm sorry for technical issues that I have already faced, and I can finish my presentations. I was remaining with only one slide because I was discussing about the challenges that the authors have already seen for the detections of cytokines. I've already discussed this one. I was discussing about I was already discussing about the sweet collection because some biosensors, they are unable to differentiate clearly the old sweet and also the new ones. So that was one of the challenges that they were already facing. And also the device stability during movement. So because some of those wearable biosensors, they may be on someone's body, they may be inserted on the body, or they may be attached, or others they can be printed on the clothes so that the wearer, someone who is going to use it, can move with it. So they are still having the challenge for the stability of those wearable biosensors. And lastly, according to the authors, they used to have the future directions. What can we expect in the future? In the future, according to the papers, they have already said that we can expect the development of more compact, sensitive, and wearable biosensors by using different different methods, different materials, different the surface, the biosensor methods that can be effective for the future. They are trying many by using the carbon nanotubes, the graphenes, different electrodes that is more effective. That is what we can expect in the future according to the authors. And again, the integrating wireless data transmission. So in the future, we can expect the influence of Internet of Things in the biosensors, where the data they can be transferred from the owner, from the patient, or from the wearer, or from the user to the health centers or any other institutions that can control that need those data to be analyzed. So we can expect the remote diagnosis of disease. So that was the end of my presentations. If you have any questions, you're gonna ask me. Thank you for giving me this another chance. Thank you.